Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture on time series modeling and forecasting. The title of this talk is Components of Time Series, and then in this talk I will discuss decomposition of time series into various components. Traditionally, before the emergence of Box-Jenkins approach, the popular approach for analyzing a time series was to decompose the time series into its various components, and those components are decided on the basis of how the time series is behaving in a long run or in a short period. Various components of the time series are secular trend, seasonal component, cyclical component, random component or irregular component. We denote the secular trend by TT, seasonal component by ST, cyclical component by CT, and random or irregular component by IT. We have to decompose time series into these four components. What are these components? That I am going to discuss in detail later. Among all these four components, the first three components TT, ST and CT represent the systematic part of the time series. Suppose we denote the time series by Y, then first three components denote the systematic part of Y, and these three components are due to the permanent causes, and these three components are predictable. Whereas the fourth component IT unpredictable, it is the random component or irregular component. In the context of processing, the first three components TT, ST and CT denote the signal, whereas the fourth component IT denotes the noise. Now, what are these four components? I will discuss in detail. The first component is secular trend. Now, secular trend is a long term movement of a time series. Just for example, if you take the population of India, so we have census after each and every 10 years. You take data on the census of India for the last say 50 years or 100 years, and you plot those data. Then you will observe a particular kind of behavior, and that behavior is with the passage of time, the population has a tendency to increase. In a long population is increased. So, this kind of tendency is called the secular trend. A seasonal variation is a regular periodic variation with period of cycle within 1 year. So, it is a periodic variation. For example, if you consider the sale of umbrella, monthly sale of umbrella in a departmental store, say, then you will observe that during the rainy season the sale increases, and this is a periodic phenomena. This happens each and every year. And what is the reason behind this phenomena? It is the season, rainy season. Cyclical variations are also more or less periodic or repetitive, but these variations are more gradual, and in comparison to the seasonal variations, these variations are relatively long term, up and down repetitive movements of the time series. And the last component is random variations, which are purely random or irregular in nature. And in any time series, these random variations are usually large in numbers, means these variations have very high frequency, but small in magnitude. So, in fact, there are two kinds of random variations, large in number of irregular variations of a small magnitude, and then sometimes you also observe few irregular variations of large magnitude, but for short duration. Such kind of irregular variations which are of large magnitude, but just occur for shorter duration are caused by unforeseen and uncontrollable events such as earthquakes, wars, floods, etc. For example, during the second wave or first wave of COVID, the number of patients who have to hospitalize has tremendously increased, but that increase is just for a shorter period. Now, this kind of variation is because of just some unforeseen event. So, this variation is irregular variation. In fact, these are the variations, the random variations which make the time series stochastic or random variable. First three variations, trend, seasonal variations and cyclical variations, are regular variations. Those three variations are predictable, but this fourth variation, random variation, makes the time series stochastic or a random phenomena. And then traditionally there are two models which have been considered to decompose the time series. We write the time series y t either as the sum of four components. So, y t is equal to t t plus s t plus c t plus I t. So, this kind of decomposition is called additive decomposition. The second decomposition, which is called the multiplicative decomposition, writes the time series y t as the multiplication of these four components. So, y t is equal to t t into s t into c t into I t. Now, in practice the problem is whether you should go for additive decomposition or multiplicative decomposition. So, this you have to choose. Then how to choose one of these two decompositions? So, whether you have to select additive decomposition 1 or multiplicative decomposition 2. So, we consider an example. Now, suppose in every month of October, a car company sells 10,000 more cars than in November. Now, in this example, in comparison to November, the car company sells 10,000 more cars in October. So, the seasonality is additive in nature. Sale is increased by 10,000. So, 10,000 more cars are added in the. Now, suppose the car company sells 20% more cars in the summer months than in the winter months, then the seasonality is multiplicative in nature. So, in this case you are giving in some sense the proportion of increase or percentage of increase during summers. During summers, the sales are going to increase by 20%. So, you have multiplicative seasonality. Additive seasonality can be represented as an absolute amount. So, in the example it is 10,000 absolute amount, whereas multiplicative seasonality can be represented as a constant factor. 20% is a constant factor. So, sales are going to increase by a constant factor, that is 20%. Now, we observe the magnitude of seasonal fluctuations or variation around the trend component, because your time series not only has seasonal component, it may also have trend component. So, better if we observe the magnitude around the trend component. Now, if it does not vary with the level of the time series, select additive model, and if it appears to be proportional to the level of the time series, then you have to go for multiplicative model. Well, I will explain these 2 points later on with the time series plots, when to select additive model and when to select multiplicative model. One of the alternative is, if you do not want to use the multiplicative model, then it may be possible for you to transform the data using some suitable transformation. Usually the log transformation works, and then after transforming the data, you can convert the model into additive model. So, we transform the data until the variation stabilizes over time, and use an additive decomposition for transformed data. So, if you are using log transformation, then log yt is equal to log tt plus log st plus log ct plus log it. So, after taking the log transformation, you have converted, you have transformed the multiplicative model into the additive model form. I will again come to this point later on when we will consider the seasonal component in detail. Now, I will show you the graphs of different time series models, which will help you to understand how different time series have different kind of variation. So, time series consist of distinct patterns or mixture of patterns. It is not a single pattern which is causing variation in the time series. It may be a mixture of different patterns. It may be a mixture of trend as well as seasonality or cyclical component, and of course, randomness will always be there. And once you identify these patterns, these components, then it becomes easier for you to make the predictions. Now, here is a graph of electricity generated in India in terawatts per hour, and I have taken this data from the World Bank site. Data is from 1985 to 2018. So, it is a simple plot of the time series. Now, from the pattern of the graph, you observe that the electricity generation has a tendency to increase. In the graph, it does not show any kind of seasonality. Of course, we have taken annual data, so we cannot capture within year movements or within year periodicity. So, that is why this time series is unable to capture the seasonal fluctuations, but it has increasing trend. Of course, sometimes electricity generation decreases also in some particular years, but in general it has a tendency to increase. Now, here is a graph of air passengers data set, which is available in our software, which gives monthly totals of a US airline passengers from 1949 to 1960. So, this data set is monthly data set. Now, since you have monthly data set, so it may be possible for you to capture any seasonality present in the data, any within year periodic variations present in the data. So, now just by looking at the graph, what can you say? The long term tendency is to increase. So, over a long period of time, the number of passengers is increasing. So, the data set has an increasing trend. Now, you also observe that without going into much detailed analysis, just by looking at the graph, you also observe some kind of seasonality in the graph. In some particular months, around the trend component, you observe some kind of periodicity. So, suppose this is the trend line, and around trend line you observe periodicity, and the period of that periodicity is less than 1 year. I will again come to this point later on. So, that is why this periodicity is caused by some seasonal factors. This graph shows you the average daily gas flow in terajoules by month on pipelines supplying the Victoria region of Australia. Now, average daily flows are given against different months. So, this is actually monthly data. By looking at the graph, you observe no trend, no increasing or decreasing pattern, but you observe a periodic movement. You also observe that the period of these oscillations is less than 1 year. You observe that each year in the month of April, the gas flow decreases. Each year in the month of November, December, it increases. So, this kind of pattern you can easily observe by looking at the graph. Now, this is the time series plot of data sets on the concentration of carbon dioxide in the atmosphere made at Mauna Loa from 1959 to 1998. This data set is also available in R. Again, in this data set, you observe a long term movement. So, you observe an increasing trend. Now, along the trend, you also observe periodicity. So, again actually the period of oscillations is less than 1 year. So, it is because of seasonal variation. Now, you compare this graph with another graph which I displayed here. Both the graphs have seasonality, but then what is the difference? In this graph, the magnitude of seasonality is increasing. So, for this data set, suppose you have to select one of the two models, whether you should go for the additive model or multiplicative model. So, naturally, in this graph or for this data set, you have to go for multiplicative model, whereas for this graph, again you have seasonality around the trend component, but magnitude of the seasonality remains constant. So, for modeling this graph, you have to select additive model. Again this first graph shows the US 10-year treasury yield in percentage. In this graph, actually you observe some kind of decreasing trend. Of course, this is just 10 years data. So, on the basis of 10 years data, you cannot say for sure that in the long term it has decreasing trend, but at least for this 10 years data set, the time series is showing decreasing trend. Then this is annual data, and around the trend you observe some kind of periodicity also. The period of these oscillations is more than 1 year. So, this periodicity is not caused by seasonal factors, this is caused by cyclical component. Then this is the data set of annual precipitation in inches in London. This data set is also available in our software. In fact, the data set is not showing any trend. Of course, you cannot observe the seasonality because the data set is annual. So, any variations, any periodicity which is within 1 year, you cannot observe on the basis of this time series. Now, this is the reason why one has to be very careful while selecting the period between the two time series observations. If you want to observe the seasonality, then you must go for monthly data set or weekly data set or quarterly data set, depending upon what kind of periodicity you expect in the data. Now, whether this second time series has any regular variations or not, for that purpose you have to go for detailed analysis. As such, you can't say much about these variations. These variations look more like irregular variations, but once you do the detailed analysis, then you can say with more surety that whether these fluctuations are actually random or some kind of pattern is available in these data set. Then now we come to this graph, which shows the forest cover area of 3 countries in terms of percentage of land area. This data we have taken from the World Bank site. Here the blue line denotes the forest cover area of India. The orange line shows the forest cover area of Australia, and the black line shows the forest cover area of Africa, eastern and southern Africa. Now, at a particular point of time, say on a particular years, if you take say 2010, then the figures of a particular year shows that the percentage of forest land in Africa is the maximum. This is the kind of information you get from the cross section data. But if you consider the time series data and look at the nature of time series data, then you can say that the percentage of forest cover area of Australia has a long term tendency to remain constant. It is almost constant. The percentage of forest cover area of India has increasing trend, whereas the forest cover area of Africa has a trend to decrease. So, the kind of information which we get from the time series data, you won't get from the cross section data. Cross section data can compare the figures of 3 countries for a particular year, but time series data, on the basis of time series data, you get the information whether the data have some increasing or decreasing trend or not. Now, we come to the secular trend component. We consider this component in detail. So, again the secular trend is a general systematic gradual change over time. It is a long term movement. So, trend exists when there is a long term increasing or decreasing pattern. If the data in the long run has a pattern or tendency to increase or decrease, then we say that the data has a trend, long term trend. This trend component may be linear or non-linear. So, in several examples which we have discussed earlier, you have observed that the trend is non-linear. It might change direction from an increasing trend to a decreasing trend or vice versa. So, this also happens. There might be several reasons for the change in direction. This happens when the trend component changes direction from increasing to decreasing or from decreasing to increasing. Now, this kind of behavior to change the direction is called a structural change in the trend. What are the factors responsible for such kind of movement? Naturally, those factors are long term factors, say long term effects of socio-economic and political factors, or so if there are some changes in the economic policies or there are several social factors because of which the time series develops a tendency to increase or decrease. For example, global warming. Because of global warming, you may find some kind of long term tendency to increase or decrease in global temperature or rainfall, etc. Environmental factors such as global warming, which I discussed earlier, or air water pollution also. Increase in the patients of some airborne disease in Delhi. Now, since the pollution level in Delhi is constantly increasing, so it may be causing increase in some diseases, some lungs related diseases which are caused by air pollution. So, number of if you take data on the number of patients visiting the hospital because of some lungs related diseases, and if you take annual data, then the observations may have a tendency to increase, and the reason behind that tendency, that trend component, is the air pollution. Then advancement in medical science. Now, if you take the data on cancer patients, say the period for which they survive once the cancer is detected and the period for which the cancer patient survives. And if you consider the average longevity of cancer patients after the development of cancer, then because of advancement in medical sciences, that period has a tendency to increase. So, you observe an increasing pattern and increasing trend component. So, a lot of information you get from the time series or run sequence plot. If you plot time series against the time, then this plot is also called the run sequence plot. So, we take observed data on the y axis against the time sequence on the x axis in the form of line chart. So, you can easily observe the trend in this series, and you observe that there is some increasing pattern in the time series. So, Actually, this is Netflix share price data from 2009 to 2018. The data has an upward trend, which you can easily identify. Not only that, this trend is non-linear. It is slightly curved in increasing means this curve, if you that's trend curve, if you observe, then the rate at which the observations are increasing, it has a non-linear behavior. So, increase show that the data values accelerate over time. So, what we observe is it has increasing trend, the trend is non-linear, and with the passage of time the data values accelerate. Now, we consider different methods for the determination of secular trend component. The simplest possible method is the method of freehand curve fitting. This is a graphical method, and in this method, first using appropriate scale, we take the time period along the x axis, and then we plot the observed time series y t on the y axis against t. Then we join the plots points by line segments. This is what I was doing in several examples. In the last slide also I did it. I joined different points using a smooth curve. So, in fact, I was using the method of freehand curve fitting. While joining the points, we use some smooth curve. Of course, we prefer a straight line, but it is not essential. And we should take care that most of the points concentrate around the curve. So, it is a freehand curve covering most of the points. So, this curve indicates the general trend of data. Of course, there are several advantages when we use this method. The method is quite simple. You can easily use it for measuring secular trend component, and in fact, it covers any kind of trend component. It does not require any mathematical calculations. It does not take much time also. It is quite flexible, and it can be used for any types of trends, linear as well as non-linear. A well-fitted trend line or curve gives a close approximation to the trend based on a mathematical model. So, if you fit the trend component using a mathematical model, we will discuss this method also in details later on. Then and if you are well experienced, then your curve may be quite close to your curve may quite closely approximate the mathematical model, the fitted mathematical model. There are several methods of this method. The method is subjective and greatly affected by personal bias. Different individuals may draw different trend lines for the same set of data. Now, this may happen in practice. Say one person is preferring one trend line, another person is preferring another trend line. Then forecasting using this method is not reliable, particularly if the person drawing freehand curve is not well experienced and efficient. Because here in this method you are not using any mathematical formula, so you do not have any precise method for forecasting, precise formula for forecasting also. If you want to do forecast, then what you are going to do? You will extend the curve beyond the range, and then on the basis of that curve you try to make the forecast. This is the same curve, Netflix data curve, and I am drawing a freehand curve. So, this shows you the trend line. Now, this may happen that some other person prefers this curve. So, different people select different curves. So, this method is quite subjective in this sense. So, this is a strong demerit of this method, and for forecasting purpose you have to extend this curve beyond the range, but again these forecasts will be subjective. So, this method is not very efficient for making the forecast. The second method is the method of semi-averages. This method is also quite simple. The main steps of this method are: you divide the data into two equal parts with respect to time. So, suppose you have 50 observations, then you divide it into 25 and 25, two sets. But if you have 51 observations, then you remove the middle observation. So, you are left with the 50 observations, and then you divide the observations into two parts, 25, 25. Remove means for the calculation purpose only. Then plot the arithmetic mean of the sets of values of y t against the center of the relative time span. So, if the number of observations is n equal to 2m, you have even number of observations, then the exact division into halves will have m observations each. So, in each half you will have m observations. Now, if n is equal to 2m plus 1, odd, just like we have taken n equal to 51, then you drop the middlemost, that is m plus 1th term. Then we join these 2 points together through a straight line which shows the trend, and the trend values can then be read from the graph corresponding to each time period. Merits of this method are: it is quite simple to understand as compared to the other methods for measuring the secular trend. In fact, the method of freehand curve fitting is even easier, but the method of freehand curve fitting is totally subjective, but this method is not totally subjective. There are several demerits also of this method. In this method, we assume a linear trend between the plotted points. So, you can use this method only when the points have linear trend, and whenever you add more observations, it requires redoing the entire computations again. Of course, this is not a big problem nowadays, because now nobody uses calculators for computation purpose. You can use different statistical softwares or even Excel. So, this is not a big issue. Now, this method is based on averages. What you have done, you have divided the observations into two parts and then you have calculated the averages for the two parts. But as you know, the averages are affected by extreme values. So is this method. So, this method is also affected by the extreme values. Now, here is an example, a very simple example. We have time series of number of TV sets which came for repair within warranty period in a service center. So, the data is for 6 years from 2005 to 2010. So, initially what we do? We divide the data into two equal parts. You have first 3 observations, last 3 observations. These are the figures of first 3 observations. So, you simply take the average of first 3 observations, which is 32 plus 33 plus 40 by 3. Or simply 35. Then the average of last 3 observations is 50. Then you have to compute the trend values corresponding to different years. Now, this value 35 is corresponding to the year 2006 and 50 is corresponding to the year 2009. So, here the trend value corresponding to 2006 is 35, corresponding to 2009 is 50. And we assume a linear trend. The time interval between 2006 and 2009 is 3 years. And the difference in trend values of these 2 years, 2009 and 2006 is 51 minus 35, which is equal to 15. So, from using these two figures, you can easily calculate the change per year, which is 15 upon 3 or 5. So, change per year in trend values is 5. And remember that here we are assuming linear trend. So, this method works only when you have linear trend. So, since change per year is plus 5. So, for the year 2005, we subtract 5 from 35. So, you get 35 minus 5 equal to 30. For the year 2007, you add 5. In general, you can compute Tt for any year by using this formula. Tt equal to 35 plus T minus 2006. So, for 2005 it is T minus 2006 is equal to minus 1. So, 35 minus 5. For 2007 it is 35 plus 2007 minus 2006, which is 1. So, you get 40 and so on. This is how you can compute different trend values. And you can plot these trend values which you have obtained using the method of semi-averages. So, trend line is linear and you get the trend values corresponding to different time points also. And in fact, you can use this straight line of trend values for forecasting purpose also. Because in here, suppose you want to forecast the value for 2011, then 2011 minus 2006 is equal to 5. So, t minus 2006 is 5. The estimated value of t for 2011 is equal to 35 plus 5 into 5. So, it is quite simple. Today we have discussed different classical procedures. So, in this lecture we have discussed how the time series can be decomposed into various components. In fact, the graphical representation of time series plays very important role in identifying these components. These 4 components are trend components, seasonal components, cyclical component and irregular component. Using these graphs, you can easily identify whether your time series is mainly composed of a single component, it has just trend component, or it has just seasonality but no trend, or it has only periodicity, or it looks more or less like a random series. But still, for the detailed analysis, for the more accurate forecasts, you require some precise procedures, because on the basis of these graphs you can make some comments. You can say that well, your time series is a mixture of seasonality and trend. Your time series has nonlinear trend, or your time series has trend which changes direction, but you cannot use these graphs for forecasting purposes. For forecasting purposes, you require some precise mathematical procedures which can decompose time series into the 4 components, which can give you some precise formula for obtaining different components. And then it becomes easier for you to use those formulas for the prediction purposes. Now, this method of decomposition of time series into 4 components was very popular before the emergence of Box-Jenkins approach. So, that is why I am covering this part also in detail. In the next lecture, I will consider the detailed procedures, 2 more procedures for obtaining the trend component, the method of mathematical curve fitting, and the method of moving averages. In the method of mathematical curve fitting, we represent the trend component either by a straight line or by some other appropriate curve. It may be a quadratic curve or cubic curve or exponential curve. So, it depends upon the nature of the trend component, which curve you have to select, but once you select a proper curve for fitting purpose, you can use a proper method like the method of least squares for obtaining the trend component. And I will discuss this method in the next lecture. And then in the next lecture, I will also consider the method of moving averages. The method of moving averages is slightly different from the method of semi averages. In the method of semi averages, what we do? We divide the observations into two equal parts, and then assuming a linear trend, we calculate the simple arithmetic mean of first part, observations of the first part and the observations of the second part, and then on using these two averages we plot a straight line which represents your trend, but the method of moving averages is slightly different, and I will discuss it in the next lecture. Using those methods, the method of mathematical curve fitting or method of moving averages, you not only get precise values of the trend, those methods are more objective, not subjective like the method of free end curve fitting. And you get exact formula for calculating the trend component. So, that will be the main focus of my next lecture. So, although the method of free end curve is totally subjective, and for predicting the trend we do not use it, but you cannot discard it totally. Still, it is useful in getting an idea of trend or an idea of the mathematical curve which one should fit in the method of mathematical curve fitting by using the plotted freehand curve. So, it is not totally useless. It gives you a preliminary idea of the mathematical curve to be fitted for the data, which is appropriate for the data. Similarly, the time series plots also give you idea of the magnitude of seasonality, or whether you should go for the additive model or multiplicative model, things like that. You easily get the idea whether you should go for the multiplicative model or additive model using the graph that I demonstrated using many examples. So, while analyzing a time series, these kind of curves give you a preliminary step for the detailed analysis. From the curves you get the basic idea in which direction you should go. Of course, for the detailed analysis of the seasonal component, or for obtaining the seasonal component in a more precise way, in a more mathematical way, we have different methods, which those methods also I will discuss in later in other lectures. Okay, thank you.
Hello, good morning everybody. I am Raghunandan Sengupta. So, I will just give you a very brief excitement area of finance, which is quantitative finance, and that has a huge market starting around about 10 years back, and it is exploding exponentially. So, what do we mean by quantitative finance? Quantitative finance is actually the application of different mathematical and statistical techniques in the area of financial markets, be it say for example derivative pricing, be it in the area of say for example portfolio management, be it in the area of asset liability management, be it in the area of portfolio management. We see that the application has exploded in such a way that there is a huge opportunity for people who have a quantitative background in mathematics and statistics. They can utilize those in the area of finance, but obviously with some prior knowledge of finance as a subject. Now, when we say about quantitative finance, as I said, it is an area of applied mathematics and statistics applied in financial markets. Use of different areas, if somebody is interested to know, we have stochastic calculus, we have derivative pricing, we have operation research, we have quantitative techniques like differential equations, stochastic calculus, time series, and they are heavily used in the area of quantitative finance as I mentioned. Now, we all know that in 1997 the Nobel Prize in Economics, so it is basically the Nobel Memorial Prize in Economics was given to the work of Merton and Scholz in the area of derivative pricing, and after that there has been exponential increase in the area of quantitative techniques in quantitative finance and in the area of different type of derivative pricing. With the advent, moreover with the advent of high-ended and sophisticated computing data, big data has come in a very big way, where application areas starting from computing, from different type of algorithm design have been taken up in such a big way that nowadays at least we are able to understand that how high frequency data algorithm trading can be utilized using the concept of quantitative finance in the area of finance as such. But there is a flip side also, obviously when there is a huge amount of development. So, obviously due to some regulation errors or something, there has been some pitfalls, which I think is should be a bullet point for people who are really interested to take up quantitative finance, they should be aware. So, consider the financial crisis in 2008 and later on, and we are seeing different banks are failing, different financial institutions are facing a problem, countries are facing a problem like in Europe, in USA. So, what should be done? So, the main thing is that even if you know the technique is best for people who are investors, who are private players, organizations like banks, governments should use these techniques in a very somber manner, such that the application areas of quantitative finance using the techniques which we learned can be utilized in the best possible way to garner the overall the in-depth knowledge a person has in trying to utilize these quantitative techniques in finance. And I am sure that people who have the background, who have the knowledge, who have the sophistication, who have the knowledge of the society can definitely use quantitative finance in a very big way in trying to make their mark in this exciting field, which you are going to see in years to come. And I am sure it will be a very exciting learning tool for all the participants who will take quantitative finance as a subject in years to come. Thank you, and I wish all the participants all the best and best of luck for the programs they will take. Thank you.